I want to introduce my students here, Gertie Algil, Voltaire Balagod, and Alex Whitcott. These guys and the other two teams will be presenting their projects, their final projects for TV at the end of their third year of communications technology program. And I think you'll agree with me after you see this that it represents a very high quality of standard we come to expect from our students here.
We're from the Seneca Boom Diagnostics team. And first, I would like to present our project outcome. We developed a methodology that will allow any user to use our testing board without the supplied detail manual, as you can see in my hand, and the supplied supplementary CD as well. Now, I will talk a little bit about the background of this whole project. This is a joint venture between Seneca College and Boom Recording Studio, which is ran and owned by Mr. Frank Vanna. This is a fully functional studio which consists of a 56-channel audio mixing console. As you can see, on the left side of this picture, we have 32 mixing channels, which are used for live instruments and voice recordings. On the right side of this console, over there, you can see the rest of the 24 bus channels, which are meant for final editing before recording on the tape machine, CD, or hard drive. Next, my partner Gordell will present all the major problems of this console.
Well, one of the major problems we had with this console was that it had a tendency to overheat. The main reason for this overheating was its original design. The audio strips, which are located on the console, are physically placed too close together, and all of the components given produce a lot of heat. In addition, the console has very little ventilation. This causes certain components, such as capacitors, to easily dry out and need to be replaced occasionally. Secondly, this board has a problem with the mechanical switches that are located on the audio strips themselves, as we'll show you in our demonstration. They also have to be replaced occasionally because they wear and tear very easily, and because they're constantly being applied as the technicians over there or whoever's working with the board has constantly pushing the switches. Taking these two problems into consideration, we can say that this board is a high maintenance board. Therefore, Frank Venna, who's the owner, approached our group with a possible project opportunity. He stated that he needed a way for us to design a method that would allow any user to test and repair the audio strips of the board, but not interfere with the console's day-to-day uses, because that's its main console and you can't afford to have any downtime. Therefore, our first strategy to attack this project was to conduct lots and lots of research. We started off by studying the factory's owner manual of the console, secondly the schematics, and then we compared those to the actual strip to get an idea of the layout of the circuitry we were dealing with. And lastly, we need to have understanding of how the recording studio functions. We needed to know the various devices that correlate together in order to produce something like a soundtrack or any sort of product from a recording studio. Based on our research, we were able to come up with some ideas. These ideas helped us develop our test manual and our testing kit. Now my partner Voltaire will discuss some of the obstacles we ran into as we were designing the manual and our testing.
Yeah, thank you, Gurdjieff. So as Gurdjieff mentioned, we generated a couple of ideas for our project, which seems simple at first, but as everyone knows, a simple project always runs into a lot of problems. So a couple of our major problems were trying to decide where exactly to test on the audio strip. As you can tell, the circuitry looks fairly complex. So the first thing we did was discuss with Mr. Frank Venna, who outlined to us which section of the board we should place our primary focus on. Based on his description and based upon our research, we were able to locate the specific circuitry of the functions on the strip itself. Once we located the circuitry, we could then designate certain components to be used as our test points. The next major problem we had was trying to determine how exactly do we test these points. The console and the strip were powered by this main power unit in the studio. Based upon its reference material, we learned that this power unit provides a plus and minus 18 volts along with a 5 volt to 0 volt logic power to the strip, also with certain signal levels. Once that was learned, it was a simple matter of acquiring the proper equipment such as a portable power supply and function generator to work with our test board. Now Alex will get into a little bit of the details of our test board.
Throughout our project, we had 3 designs in total. Due to a lack of previous knowledge of those strips, our first design consisted of 128 pins coming out of the strip. That was necessary for us to find all the test points, the voltages, and the signals coming in and out of the board. Then, our second design was about 1/3 of the size, and it consisted of only the necessary points we needed. And finally, we created a full enclosure for the strip that provided us with a fully secured bay that would allow it to perform tests and different diagnoses with a very short time.
So with our test board in place, we then placed our focus on a manual. But before we could actually put something together, we had to determine what the correct values would be. So the first thing we did was we took an actual service strip, attached it to our board design just to get a general idea of how it would interact with what we had developed. Once we were comfortable with that, we then took operational strips from the console itself, performed numerous tests, and generated a list of values under certain test points. From this list, we looked for a consistent number, which we then implemented as our expected result in our manual. This is an example of our workstation. It may look chaotic, but a lot of good came out of it. So once our values were determined, we then started putting together an actual manual. It included various materials such as an equipment list, so that any user who picks it up knows exactly what they need to have in order to do the testing. Of course, they have the diagnostic procedure itself to do testing on the mix strip performed on our testing board, as well as bus strip testing, which is done on the actual mixing console itself. And accompanying these diagnostics are also the repair guides, which help outline to the user which sections of the strip they need to focus on and which components need to be changed. Along with a written manual, we have a supplementary CD. On this, we include an inspection sheet, which the user can use to fill out as they're doing a certain test, as well as keep a history of the strips. Also, there's various reference material they can use, as well as tutorial videos to help them along the way, such as this one right here.
An example of a path switch includes this low path switch. It produces crackling noises as you are pressing it down. Example of a good switch includes the sub-mix switch. There's absolutely no crackling at all.
For some of our future recommendations, our group discussed that we would, in the future, want to design a test procedure for the rest of the functions of the mix strip, and secondly, design a test procedure and another test bay for the bus side of the console. And finally, in the near future, we would like to design something that would, another test bay which would be fully automated, interfaced with a device such as a lab jack, and that device would allow test results to be automatically stored onto a computer for later review, and in turn, we wouldn't need to use inspection sheets at all, and it would remove clutter and such. And also something that we discussed was trying to develop a method to provide better ventilation to the console, thereby reducing the maintenance that's required. Finally, we just want to acknowledge some of the support we've had throughout the project. Obviously, Boom Studios, Frank Benna and his partner John, Seneca College, Professor Chris Rogers, Eddie and the Seneca PCB team, and especially to Rose, who's been very helpful with the administrative side of things. And special thanks to OC Finance Department for funding our project and making this a possibility.